Hello there, good evening. Let's first wait a few minutes to see if anyone will join, and then we will begin. Okay, so once again, hi, I'm Jerry, and I'm the director for physics at Logistem, and today we're going to do a introduction to fluids, and we're not going to use calculus today, so we're not going to go that deep in, but the purpose of this session is is for you guys to get like a basic and fundamental understanding of how fluid mechanics work. So we will begin with what is a fluid? When we say fluid, we normally refer to liquids, but in physics, fluids is basically any substance that takes on the shape of its container or can continually deform based on stimuli from its environment. So solids obviously cannot be a fluid, but both liquids and gases can be fluids. And fluid mechanics is basically the study of fluids at rest and in motion. So this basically divided into two categories. The first one is fluid statics, static as in like something stays in the same position as like it just remains in the same position. So that's basically studying how fluids behave while at rest. And the second type is fluid dynamics, which obviously anything that ends in dynamics is basically studying something in motion. So fluid dynamics is basically the study of fluids in motion. So some main principles of fluid dynamics include one, the fluids are basically the substances that flow when an external force is applied to them. So they have to like act when like a force is applied, like the entire volume of fluid has to move. Liquids and gases are obviously both fluids, as I said earlier on. It's not limited to just liquids. Fluids do not have a definite shape like solids. When placed in a container, they conform to the shape of that container. So, although you can obviously observe this with water in like a water bottle, but it's the same case for gases as well. The total force exerted by liquid at rest on a given surface is called thrust, and thrust plays directly into pressure. The SI unit of thrust, obviously, since thrust is a type of force, so we will use the SI unit for force for thrust, and that's Newton. For pressure, pressure is force over a certain area. So you would use a Pascal, as we will see earlier on, which is basically 1 Newton divided by 1 meter squared. A faster moving fluid has less pressure than a slower moving fluid. So basically the velocity of a fluid in like a closed system and like its pressure, like the pressure it exerts, or that. So basically these are inversely related. We will also talk about Archimedes Principle. So Archimedes Principle, you've probably heard this before. It's obviously that like age-old story of like when Archimedes was a great mathematician in the class when like classical civilization was in its dominance. So basically at the time of the Greek and Romans, around like the 200s BC. He lived in, I believe, Sicily, and back then that was ruled by a tyrant, and the tyrant received a crown from a goldsmith, and he doubted whether or not the goldsmith had embezzled pure gold from him. Basically, he gave the goldsmith gold to make a crown, and the goldsmith used that to give him a crown, but he wasn't sure if that crown was made out of pure gold like he wanted the goldsmith to make. Basically the question was, did the goldsmith use an impure alloy of gold and some other material and then keep the rest of the excess gold for himself, which is a crime. So Archimedes was pondering this question and entered a full bathtub, and the water overflowed naturally. And he had a moment of eureka, which is Greek for "I found it," and he like ran directly to like the palace because he had discovered how if you submerge an object into like a fluid, the volume displaced is the same as the volume of the portion of the object that's submerged. Nowadays, we use this, we state this a bit differently. Instead of volume, we use buoyant force, although both still apply. So basically buoyant force, you probably have heard of the word buoyant before. Buoyant means something floats. So when you submerge something solid or like a less dense liquid in another one, there will be a force exerted by the liquid on the bottom that tries to force like this object towards the top of the fluid. And this type of force is called buoyant force. It doesn't matter whether or not like the object is sinking or like completely submerged or like partially submerged. This buoyant force will always be there. and it's always directed up towards like the surface of the object. The principle itself states that the buoyant force on a submerged object is equal to the weight of the fluid that's displaced by the object. So when an object is dropped into that water, obviously some of the water is displaced, and at the same time, buoyancy is basically like pushing the object up, and that alters like its relative weight to the water. And so if the weight of the object is heavier than the amount of water it displaces, that object will obviously sink because like it's too dense. And so that weight just can overcome this buoyant force. So the object will naturally accelerate downwards. And if the object of the amount of water displaced is equal to the weight of the object, or then it would be the object would float. We would eventually reach an equilibrium where there's no net force, and it will float in that position. Although this can be simplified down to like whether or not something sinks or floats can be determined by its density. So like, for example, water has a density of if I believe correctly, 1,000 of kilograms per cubic meters, although please don't quote me on that. And if something is greater than that, it will sink because it's more dense than water, so it will fall to the bottom. The buoyant force will always overcome the weight will always overcome the buoyant force, and if it is less, it will just float. If no matter how much you try to like push it down, it will float back up. Buoyant force can be calculated by the formula rho GV. So here rho is basically a Greek letter. It's the Greek letter R, but we write it like a curved P. And this always represents density in 3 dimensions. So obviously, since like things are like have surfaces and stuff, it's 3-dimensional. So we use the character rho. So the rho here refers to the rho of the liquid, not the object. G, or little g as I like to call it, is obviously just the acceleration to the gravity on Earth. That is about 9.81 meters per second squared. And then V is the volume of the object, of the part of the object that's submerged in the water. So for example, if the object is completely like, if it sinks, that volume would be the entire object volume. But if it's like the ball in this picture, where like it's just halfway floating, that V would just be half of the sphere's volume. Obviously, when buoyant force is equal to the weight of the displaced fluid, then FB would equal to MF times G, which is basically FB is just equal to the weight of the fluid that's displaced, and weight is mg, so it's mass of the fluid times G. If an object is floating, this MF can be turned into MO. The buoyant force can also be equal to the weight of, obviously, the weight of like the air minus the weight of the fluid, because that's also the apparent loss in weight of a body immersed in fluid and turned into a displaced fluid. So as we talked about earlier on, if the weight of the water displaced is less than the weight of the object, then that object will sink. Otherwise, the object will float, and the weight of the water displaced will be equal to the weight of the object. So you might be wondering, like, back to that density question. We know like a lot of boats today are made out of like metal, like extremely dense and heavy metals like steel. And we know like something like a steel ball will naturally sink in water because steel itself is very dense, way more dense than water. So how can a boat float? So this question, obviously, now that we know Archimedes' principle, know that it doesn't entirely rely on density, and you have to take into account displaced fluid and buoyant force. So here in this picture, we have a cruise ship. And yes, we know cruise ships are extremely heavy. And if you condense all that mass of a cruise ship into like a single sphere, it will sink. But the reason why the ball sinks and the object floats, even though they might have the same amount of mass, but the same type of material, is that for the ball, the sphere has like for the amount of material is basically almost as compact as possible. So it's extremely like tight knit, like the sphere is very tight knit and very dense. And so when you submerge it in the water, it will displace less water than like any other shaped object. So due to Archimedes Principle, the weight of the water displaced will be less than it will be more than the buoyant force, so it will sink. And so if like once again, if the volume of water displaced by the steel ball weighs less than the ball itself, the buoyant force will be like less than basically the weight of the ball. So the ball would have a net force facing down, so the ball sinks. So like this one is a simple question if you know like Archimedes principle. So what is the buoyant force on a boat that displaces 65 cubic meters of water, in which here we're assuming 1 cubic meter of water weighs 9,800 newtons. So, so here we would use FB, the buoyant force would be MFG, and that's the same thing as the MOG. So we know FB over M0 is just 9,800. So you can plop in your volume, and we get this, 637,000 newtons. Another thing we tend to examine in fluid dynamics is fluid flow. So obviously, if a fluid's in motion, it's flowing, and there's different types of flow. So there's steady flow, in which like the movement of a fluid does not change over time, and the rate of flow just remains constant. This occurs in like if you like turn on the tap to like its maximum flow rate, it will flow steadily, even though it may not do so when you barely like turn the tap on. Unsteady flow is where the movement of a fluid and like the rate of like the flow rate fluctuates with respect to time. There's also different flow types. So you have laminar flow, which is a steady and smooth flow of liquid. So if you like were to draw the current of the fluid, you would see straight or like lines that basically go in a single direction. They may not necessarily be straight, but it at least goes in a single direction and does not like form eddies or like whirlpools or like things like that. That occurs in turbulent flow, which is an unsteady, irregular, and chaotic flow. A lot of like the wind is an example of turbulent flow because it often forms like cycles within the atmosphere. You also have pipe flow, which is basically when a fluid is moving through a pipe and basically while moving, it's in contact with a immovable boundary on all sides. And you also have openness channel flow, which is basically a type of flow where there's at least one free surface that's not in contact with a rigid boundary, such as like water moving through a river or like rainwater traveling down through to the gutters. So here we have like a diagram of laminar and turbulent flow. So you can see in like a scenario where like water is getting pushed through a pipe, this is typically a laminar flow, where you can see the direction of current is straight and in one direction. This is in contrast to turbulent flow, where you can see like the directions of currents of like and like the particles that make up the fluid travel in like a lot of different directions, and there's like an inherent chaos in the diagram. So that's like one way you can distinguish between the two types of flows. Alongside Archimedes principle, we also have Pascal's principle, or like Pascal's law. Pascal's law talks about pressure, and pressure, like I hinted before, is basically force over area. It's a measure of how much force is applied over a given area. And the formula is P is equal to F over A. So pressure occurs from like the tiny particles in like a fluid continuously hitting like a single boundary, like that's your area. Once during this collision of like the particles that create this boundary and like the particles that make up the fluid and that are in motion, impulse is delivered during that collision with respect to the boundary, like the area. This impulse basically makes it appear like there's a net force. So this is where you can that's why like even if like there is you don't see anything like water flowing through a pipe, you may not necessarily see the pipe burst due to like high pressure, but you still know that there's pressure there because this collision always happens. Pressure obviously must be positive. The pressure applied to any part of the enclosed liquid will be transmitted equally in all directions throughout the liquid. So for example, if I have a bottle and I like let's say I have a bottle and like I open it and then I like apply pressure to this top layer of water. This like net force, if I apply any force or like anything that creates pressure, the pressure that is exerted on the fluid will spread out evenly through all the water in the bottle. It doesn't matter like what the bottle shape is or anything like that. So that's kind of like a way to see it. This obviously does not mean that like at every single point in the field, the pressure is, no, every point in the fluid, that the pressure is exactly the same. But it means that if the pressure is increased at one point in the fluid, it increases by that same constant amount at all the other points. So basically, one application of this is with pistons. So pistons is obviously, you have two ends and one end has a force applied to it, and in between these two ends, there is a fluid, and it's basically applying that force on one end causes like the other end to raise or lower accordingly. So here we have an example of a piston. This is a hydraulic lift. So there's an original force that's applied to like one end, and let's call this like F1. F1 can obviously be expressed as P1 times A1, and then P1 would be equal to F1 over A1. At some point, we know that there's a force that's exerted on the other end. Let's call this F2. Obviously, we divide by A2, the area of the second piston, and we will get P2. So we have a P2 equals F2 over A2, and P1 is equal to F1 over A1. By Pascal's principle, we know that these two pressures have to be the same because any like additional pressure that's like created by this F1, this P1, this has to be distributed evenly, so P2 will be the exact same. Thus, this actually gives a relationship between the amount of force that gets exerted by like each end of a piston and like the areas of the piston surfaces, or like. So for example, we have this problem here. If a pair of pistons are connected on either end of a hydraulic tube, where the first one has an area of 0.2 meters squared, and the second one has an area of 4 meters squared, If a force of 30 newtons applies to the first piston, what is the force exerted by the second piston on a mass that rests upon it? So here we know that F1 is made to be 30 newtons. So we will say this is equal to 30 newtons. And then A1, obviously we are given this, A1, and this is 0.2. We also know A2 is equal to 4. Let me undo that for a second. But we know this one to be 4. Like we have in that from that diagram earlier, by Pascal's principle, we know P1 is equal to P2 on each end of the hydraulic lift, or in this case pistons. The pressures have to be the same, so you can express P1 as you can express both types of P as the quotient between F and Q. So F1 over A1 is equal to F2 over A2. And then here you can just substitute in values. So we have 30 here over 0.2. This is equal to F2 over 4. Here we can solve this using cross products, which is basically if you have this type of proportion, you can multiply in this manner, and like these two products that are expressed by these red circles, these have to be the same. You can basically get this by multiplying both sides by 0.2 times 4. So we have now that we have 30 times 4 is equal to 0.2 is equal to 1/5. So I will write this as such. So this will be equal to F2 or 5, and then we can carry the 5 over. So we have 30 times 4 times 5, this is 20. 30 times 20 is equal to 600. So we now know that 600 is equal to F2. Thus, the force that's exerted by the second piston is equal to 600 units. Here the units is units, so that's your answer. So we have another problem here. So here we have A1 is equal to 10 meters. Oh, they switched in the diagram, but A1 or area 2 in this diagram is 10 square centimeters, and then A2 or A1 in the area 1 in the diagram is 250 square centimeters, and they're connected by a single pipe that's filled with a fluid. The two pipes are fitted with weightless pistons that are free to slide frictionlessly inside the apparatus, and the pipes are filled with an incompressible fluid, and the bottom of the pistons are directly aligned with the fluid level. Now, obviously things would change if the pistons had weight. So we are like, this condition basically makes it idealized to directly use the P equals F over A equation, because if the things had weight, we would have to add on the weights to like the mass of anything on top of it, because that also has to be accounted for. And if the pipes are basically have a compressible fluid, this wouldn't work, because that like an entirely different equation will apply for compressible fluids. So having Pascal's principles like that can be applied in this way is kind of just assuming that the pipes are filled with an incompressible fluid. But anyways, if we have 5 kilograms that are it's basically if 5 kilograms is placed on the smaller piston, how much weight can be supported on the other side? Basically, we have to use two equations because we know P is equal to F over A, but we are not given F inside the problem. So we have to use the fact that here, since we just have something on top of the piston and it's pressing down on the piston due to gravitational force, we are assuming F is just weight. It's just the weight of the 5 kilogram object. So if we substitute F is equal to mg into the P equals F over A equation, we get P is equal to M1G over A1 for like the first piston for the first disk, and then P2 is equal to M2G over A2 for the second one. And obviously here by Pascal's law, P1 is equal to P2 because it's the same body of fluid. So we can set these two equal to each other. So M1G over A1 would equal to M2G over A2. We can cancel the G's because they're constants. So we get M1 over A1 is equal to M2 over A2. And then we directly substitute things from the problem that we know of. So we know A1 was 250 centimeters squared, and M2 was 5 kilograms because that was the weight. A2 was given to be 10 centimeters squared. So we just multiply both sides by 250. So we get M1 is equal to 250 times 5 over 10, which is the same thing as dividing by 2. So we get the weight, or no, the mass of the mass that's on the other side to be 125 kilograms. Pressure in liquid depends on the depth. So if you have like something that is submerged, up until now we've been doing things that are like not submerged in fluids, but when something gets submerged in a fluid, the depth, it's directly proportional to the density of the fluid and depth. So here we must differentiate between two types of pressure. So because we know Earth has an atmosphere, you have to account for atmospheric pressure when we are considering any type of scenario where we have to calculate the total pressure. So we have two types of pressure. We have atmospheric pressure, which on Earth, the pressure that is exerted by the atmosphere on the surface onto like the surface of the Earth is about 1.01 times 10 to the power 5 pascals, which was the SI unit of pressure. We also have to account for gauge pressure. Gauge pressure is it basically doesn't depend on absolute pressure, and it's basically just measured, it's basically the additional measure if there were no absolute pressure, what would the pressure of something within like like some type of fluid be? And that the formula for gauge pressure is rho GH. So rho is obviously the density of the fluid. G is the 9.8, or basically acceleration due to gravity. And then H is depth. Here we tend to think of H as height, but we're not really going above it, like the atmosphere. We're going like into some type of fluid. So here H is depth. So to find absolute pressure, which is the type of pressure that you can measure, like a pressure on like a barometer, the instrument that measures pressure. This is the total pressure. So you have to, it adds both the absolute pressure and the gauge pressure when determining pressure. So your P or your absolute pressure will be rho 0, which is your atmospheric pressure, plus rho GH. So this figure shows 4 containers that are full of olive oil. Rank them according to the pressure at depth H. And we will go from greatest to least. So anyone want to put the answers in the chat? I'll give you a few minutes to think about this one. Okay. And the answer to this is that they're actually all the same. It's because the depths at H are all constant. The only thing that basically is different from like between the 4 vessels is the shape. But we know shape has no bearing on pressure. So it really just comes down to the density of the fluid, remember? And since the fluid is exactly the same, it's all olive oil. So the density would be the exact same. G is a constant, and here H is set to be constant. It's the same depth across all 4 objects. So like these weird shapes that you see have no bearing on pressure. Okay, an empty box that's 1 meters on each side is located within its top 10 meters under the surface of a freshwater lake. What is the pressure on the top side and the bottom? So here we could use pressure is equal to rho 0 plus GH. Sorry, P0 plus rho GH. So P0 is about 1.1 times 10 to the power 3. This 1.01 times 10 to the power 5 pascals. And then plus rho GH. So here rho is, let's assume it's 1,000. Then we have times G, which is 9.8, sorry, 9.8 meters per second squared. And then we have H, which is 10 meters. So rho GH would be 98 kilopascals or 98,000 pascals. And we know, again, from Pascal's principle that everything is like distributed equally. So this pressure is constant across all edges, all like every single point on the surface of the box has constant pressure.
But since the box itself um, has length, the pressure on the bottom is a bit greater because it's a bit deeper. So pressure along the sides would be the same, be a little bit greater than the one on the top. The top has the least amount of pressure, while the one on the bottom has the greatest because it's the deepest. Um, so on the bottom, since we're saying that the box has um, a 1 meter like height, on the h on the bottom is not 10, but it's 11 now. So we multiply that out. So we get 1,000 kilograms per meters cubed times 9.8 meters per second squared times 11 meters. We get 1,007.8 kilopascals. Okay, that's we ended a bit early today, but does anyone have any questions? Uh, if there's no questions, then have a good night, everybody, and I hope to see you next time for our next physics meet. Thanks for attending.